thank you for the introduction. So I'm going to say something about embedded systems programming in C++. I have built on very small systems, but not very recently. So if I'm making a big goof, be kind. Anyway, so I'm going to give my view of what embedded systems programming is, some C++ fundamentals, and then I'm going to go into two sort of case studies. What do you do when you're really pressed for speed and space? And the other one is, what can you actually do if you can use the whole language? And that's sort of it. And the emphasis is on reliability, maintainability, predictability. Fast enough and small enough. If you want the world record in speed and something like that, you can do that too, but that's not what I'm talking about here. If it's fast enough, it's fast enough, and it has to run for a few years without anybody touching it. That's more interesting in this context. So basically, oops, this thing is very touchy. So basically, the point about embedded systems is that it's so many things. There are people, especially people who's not doing it, who thinks it's one thing and think they know what it is. I know at least as much to know that I don't know what it is. That is, there's no one thing for it to be. Programming a wind turbine and a coffee machine is not the same. There's certain similarities, like you won't get an operator on site, but things are different. Constraints are not the same. Hard real time is very important, soft real time, if you're doing a video or an amplifier, something that gives sound or music. If you lose a frame or part of a timing measure, yeah, so what? Nobody dies. And we can't hear it, we can't see it, but with hard real time, if you're adjusting the wingtips, you better get it right, precisely. So these things are different, and that's important. It also makes it really, really hard to talk about. You can talk about one specific thing. How do you program the coffee machine? That's not hard. Or how do you program the rocket motor? That is harder, but it is, again, specific. Point is, from a point of view of the language, we don't know. We don't know what you are programming and what the constraints are. And, oops, it did it again. So I'm having some technical problem here. So there's commonalities, no programmer present, and the computer is an integral part of a gadget. You don't actually go and buy an program, you buy a gadget that contains one. It could be a rocket, it could be one of those microcontrollers there. And there's common questions that we always ask. Can it be connected? If it's connected, what about security? Can it fail, and how do you recover? I mean, if you're there was that red distributed system with wheels on previous. It has more than 100 processors in it. If one of them crashes, it can get rebooted and taken over, unless it's one of the specialized ones where you only have one. So it gets how to fail and recover is always an issue. Concurrency, I just heard about embedded systems running 8 cores and using load balancing for power preservation. I'd never thought that I should use a multi-core to save power, but I was in Japan about a month ago, and they were doing it. And so if there's a human operator, the human machine interface is really critical. Think of a plane, say, or a modern car. And of course, there's all this telemetry comes out of it. This is fairly standard questions. And again, there's questions from the programming point of view. Can we afford free store, dynamic store, heap, whatever it is? I mean, one of the rules in many cases is don't malloc in any form, shape or form after the plane takes off. That's just not allowed under flight regulations, for instance. And should we worry about runtime performance? It may be that we just have to do a little bit steadily along the way, and there's other cases where we're really pressed for time. The processor is slow relative to what we have to achieve. We don't know this. This drives me nuts from the point of view of saying something general. I can't. And should we worry about memory cost? Usually the answer is yes. I mean, if you're on a satellite, you have to carry that stuff into space and it gets destroyed by hard radiation. So we need all the memory we can get, and we can't afford to send it. You want to build something and ship 100 million gadgets. Well, a little bit of memory in each is expensive. And what are embedded systems programmers? It's roughly everybody, presume everybody in this room at least. Some are professional programmers. They write code for a living. They've got an education in computer science or software development or something. And then there's a lot of engineers with no programming training and still write code. Some of the best people I know for writing code are electrical engineers, but I've seen examples of people who, I know everything, I'm an engineer. That is not a good attitude to code. The code has changed over the years, complexities have changed, techniques have changed, and if you think what you learned in assembly code back in the technical university 20 years ago, you're probably in slight trouble. And so between those two caricatures, we have everybody else. And we tend to have a mixture of domain-specific knowledge. It may be coffee machines, it may be flight controls, and our knowledge about code. And I find that most people don't really want to be C++ experts. They just want to get their work done with the least pain. And that's very reasonable and good. And I think I understand that. I'm not sure everybody who are into programming languages understand that. One thing that is driving a lot of what we are doing is complexity. The code component of our systems is steadily increasing. I mean, 20, 30 years ago, there was hardly any code in an embedded gadget. Today, it is a huge component, and of course, it's always the last bit to get finished, so we get the blame. The complexity of the code we are writing is increasing with the size of the programs we are writing, and also with the complexity of the tasks that we are trying to achieve. And so our needs change. I can reasonably confidently predict that our programs will be more complicated and more complex, more demanding in 5 years than they are today. We need all the help we can get, and that's my way of approaching the code, is that we are working at the limits of what we can handle, and we need to help there. And we need all the help we can get. So I was reading a survey recently. There's endless surveys about what people do. And this particular one said that 50% of embedded code was C, 25% was C++, and 25% was the rest. Now, I could also have picked another review that I read on the same day, which said something completely different. So, just to get me an idea about who you are, to call a little hands up to get a view. You see, I'm going to tell you what they are, and then I'm going to call it. C and C++ and other things. I have never actually built a system in a single language. There's always something else going on, if nothing else in the testing framework and such, so I assume other. C++ and not C, C and C++, and other only. So, who is doing C and not C++? Okay, who's doing C++ and not C? Wow. And who's doing both? Yeah, that's, I mean, okay, so, and other only. Okay, thanks. That gives me an idea. It also gives me an idea that you may know more than I expected when I wrote this talk, and, well, we'll see what happens. But here's my view of programming languages. There are two lines of development. There's a low line down there that deals with hardware. You want to get every byte and every cycle done well. You go from assembler to BCPL to C and C++. And then people notice that dealing with a machine directly is somewhat tedious in many cases, and you need better abstractions that are more suitable for humans for a particular domain. So it starts with Fortran, and there's John Backus up there, that gave the domain-specific abstractions for linear algebra, dense linear algebra. That's Fortran. And once that was done, everybody wanted one for their domain. So the business people got COBOL. You didn't want any of this cryptic A equals B plus C stuff that is too complicated. But you got something that was more appropriate for that domain. And in about 5 to 10 years, there was, depending on how you count, a few dozen, a few hundred languages, and the communities couldn't talk to each other because, well, Fortran, even the basic arithmetic looks different from the basic arithmetic in COBOL, and so on. And this is where Christian Nygaard come in, and Ole Johan Dahl, but there's only room for one picture here. Said, why build in the application-specific concepts into the language? Why don't we instead give people the ability to build in their own ideas, their own concepts, build their own types or type hierarchies, something like that? That's how we got Simula. And I had a problem when I started at Bell Labs. I wanted to build a distributed system, and I needed something to write the schedulers, process schedulers, memory managers, device drivers, network drivers, and such. So obviously I had to operate on the low line here. And I also needed to be able to talk about the system. There's this bit here that talks to that bit there, and they talk in this particular way through this communication infrastructure. I needed abstraction. So no language could do both, so I built C++ by taking basically ideas from Simula and putting it into C, and everything came from there later. My background started out with small machines. That up there is a small machine. It is a PDP 1170. It's Ken Thompson and Dennis Ritchie working on it. I worked on that machine too. You could get 256K of memory. Half of it was read-write, the other half was read-only. And then I worked on the LSI 11s that were smaller. So the idea of having a whole megabyte of memory is sort of, wow, lots of memory. Okay, so that's my background. And when people tell me they can't get their program running on a 10 gig machine, I scratch my head and wonder how they could waste that much. That takes talent. But anyway, this is kind of stuff. And I like bloated, I hate bloated code. I like sort of concise code that can also understand it better than bloated code. And I don't like bugs. I have repeatedly worked on systems that mustn't crash. And so that's how I get into programming. C++ has a machine model that it shares mostly with C that basically says we map straight to hardware. Hardware is right there. If I do a plus, I get the add instruction. If I want to access memory, memory is just a sequence of objects, sequence of bytes usually, and you can point to it with an address. Very simple. And if you want to combine something, if you want to build something higher, you can stick objects of the same type next to each other and call it an array. And you can stick objects of different types together, and you can call it a struct or a class. And in C++, a class and a struct is roughly the same. If you want to have something that has parts in different parts of the memory, you can point to them with a pointer. That's an address. That's it. It's very, very simple. It's about the simplest thing you see. I assume everybody here can understand this. You take a bunch of students right out of an undergraduate course, and they find this complicated because it doesn't have all the things to hiding the machine that they're used to. Okay, but this is important. There's only a snag here. That's not how a machine looked like. Machines are much more complicated than that. You know, they also were when Dennis came up with this. So this is an abstraction of the machine. This is something that allows us to think about the machine. It's something that allows compilers to generate code for that model. It's something that allows optimizers to generate good code from it. And if we have to explicitly deal with all of these things, things get complicated. So we want to hide as much of it as possible. And the C++ machine model, therefore, is an abstraction itself. And as a matter of fact, it's abstractions all the way down, because your hardware is an abstraction too. I mean, an 886 does not execute 886 instructions. There's a layer of silicon that translates 886 instructions into something that's better to execute. For those of you who are old enough, MIPS machines is what it looks like. And that way you can do dynamic scheduling and all the other good stuff. So it's abstractions all the way down, and we have to find the abstractions that are suitable for what we are doing on the machine we are doing it on. The way I look at abstraction is that I would like abstraction, but I would like abstraction I can afford. And especially when we are close to the hardware, you really don't want abstractions that adds helpful things to your data structures. There are languages that can tell you for a given object what type it is and what the time was when it was created. That just means every object has to have 2 more words. You have languages where every object has to live in the free store, so it has to have a free store header over there, and you have to indirect to get it. As far as I can count, that's just 3 words wasted. Sometimes that's wonderful. It helps, but sometimes it isn't. So what I don't want any room below C++ except possibly assembler. I wrote that somewhere in the 80s and been repeating it ever since. And it's maybe not even that. I think sometimes we can beat human-written assembler without too much trouble. I'm going to go there. Not for everything, not for machines that has instructions that we don't have, etc. That's inline assembly. What you don't use, you don't pay for. No distributed fat. And what you do use, a language feature, you shouldn't be able to hand code it any faster. And zero overhead obviously does not mean zero cost. You always pay for what you use. If you want an indirection, you pay for going through that indirection. If you want some extra data associated in your object, you have to pay for the bytes in it. Okay. I say that because I've been actually repeatedly attacked for having overhead. Yeah, of course, I asked for it. If you want a virtual function, you get an indirection. That's what it's for. If you don't want the indirection, you have a virtual function. And so know what you ask for. There is no magic. So a lot to do with software development has to do with tools. But I have about 60 minutes, and you can go to the rest of the conference here, and you can get something about the tools I just listed there. I'm just not going to there. I'm going to focus on language issues. So different kind of systems require different styles of usage. I've had lots of confused discussions. I remember one case, I was talking to a guy at a conference, and everything he said made no sense to me, and nothing I said seemed to get through to him. And I couldn't understand what on earth is going on. I mean, I'm not usually that wrong, and neither are the people I talk to. So say, okay, let's back off here. What are you programming? Oh, I thought I told you. Fuel injectors. They do this in the squirt every few milliseconds. Anyway, so I thought it was one of these big things with a screen, and that's why nothing that was said made sense on both sides. So you have to know what you are talking about. For big systems, I recommend use of full C++. It's whatever you want from the language you can afford if you have a big system. Big systems with real-time constraints, use the full language except for the critical paths. I mean, if I'm doing ultra-low latency code, the first rule is no malloc. You just can't afford that if you're counting nanoseconds. which is something I sometimes do in my day job. And you use a predictable subset there. That's fine. On the other hand, you mustn't be caught into the situation of putting the constraints of the hardest thing we do into everything we do. Because the critical path tend to be maybe 1%, 5%, 10% of the code, and we could destroy our productivity for the rest of the code. For 95% of what we're doing, we could halve our productivity by saying, really, we need to handcraft every allocation, and we have to not use anything that's possibly expensive, as if we were on the critical path. We actually have to separate what we're doing, separate the way we're thinking about our code from the critical bits where performance and compactness matter to the rest. Small critical systems, you just write the predictable subset of C++ all the time, which is basically avoid free store and usually avoid exceptions in the small safety critical systems. But about the rest of the language is pretty predictable. If you don't have more than 4 bits in a word, probably C++ is not the answer for you. And if you have 8-bit controllers, yeah, it can be done, but it's a very small subset. And basically, in most cases, I worry about space, because space is time. If I have to traverse a lot of data to get the answer, it's going to be slow. If I can be compact, yeah, I can be faster. So I'm always worrying about the amount of data we store. So I'm going to do 2 sort of almost case studies. First, I'm going to look at things where compactness matters, little gadgets mostly. And then I'm going to go and talk about when we can have the full system, full language for larger things. It roughly corresponds to what you're near that low level where hardware performance, use of hardware really matters, versus where you can use your full abstraction mechanisms. So let's look at where compactness matters. I hear reasonably often, and probably not in this room given your hands up, that C++ is inherently slower than C. I actually think on average it is faster than C. We'll get there. But let's look at a simple example. We have the smallest class I could think of. It has a constructor that does a check and stores a value, and it has an operation that does something. In this case, it squares the value. And we can do that in C++, blue, and in C, you have a struct instead, and you have 2 access functions. Now, of course, they're both C++, so it's a matter of style, but the C proponents will go for the low level. So let's look what the difference is. There is a use of the struct, and there is a use of the class. And I was very pleased to know that the compiler figured out it was exactly the same code. It's just a surface change. If you prefer the top version, and if you prefer the bottom version, you get exactly the same assembly code. I'm using Compiler Explorer here just to show the assembly code. It doesn't actually matter too much what the assembly code is, but it's about the best you can do in any way. But the fact that it's the same is, I think, the interesting bit. And now I made a difference, and they're now slightly different. And now you can see the code is different. The C++ style has an 8, where the C style has a 7. And you look, it's identical code with 1 constant changed. So, yeah, fine. You can try and remove those inline functions. I cheated. I inlined the C functions so that the compiler would generate good code. If I'd forgotten that in a separately compiled program, in many cases the C++ version would have won hands down, because there would have been function calls in the C code. But I was being fair. I put inline on, giving the hint to the compiler that it should try harder. And so there's no difference between the hand-coded version using the struct directly and using the functions for accessing it in either C++ style or in C style. And again, it just figured out it was the same. And let's go to templates. There are people who avoid templates because they're supposedly expensive and complicated. But what I've done there, instead of having the class x, I have x of t, where the member is of t, which is a parameter. And then I try that. I try with and use it instead of the x that I had in the previous slide. See, it is with x, fx. And there it is with fxx, which is the templated version. And again, it figured out it was exactly the same code and just did a jump to what I'd just done before. If there'd only been the templated version, of course you would have gotten the code that you got for fx, identically. Let's try a bit more. Let's try doubles. Doubles are not the same as ints, so therefore it has to generate different code, and floating point is a little bit more complicated than integers, but as far as I could see, for this machine, for this code generator, this is not code, and it is exactly the same code as you would have gotten if you had handwritten that x as like xd with a double in there. There's nothing particular there. So basically, zero overhead is met. It's you may be able to write better in hand code, but in any large amount of code you couldn't. So try it for yourself. So what I do when I want to know whether a feature is affordable for my use in constrained environments, I just type it in to the compiler explorer and see what happens. It does not do every machine there is, but it does do 86s and ARMs, and it does Linux, does Windows, things like that. So you can get a good idea of what a feature cost. And by the way, I don't think anybody here would make the mistake of running code without having turned the optimizer on. But I actually get into discussions with people that genuinely talk about efficiency and forgotten to turn the optimizer on and want to write fancier code to run faster. That's pretty insane. And you have to know your tool chain for this kind of thing. If you really, really don't want to compute things, you can compute at runtime, you can compute them at compile time. And there's some really nice aspects to do that. Like, you don't have to have error handling because the errors turned out to be compile time errors. Rather than calling an error handler and figuring out what to do, you can't have a race condition on a constant. If you have concurrency in your system, as most of us do most of the time these days, having calculated things at compile time so that you can't have a race condition is good. Most of the time, looking up the answer that has been pre-computed is faster than computing it. The exception being if you've been so fanatical that there is just so many different places that the access is expensive. Okay, typically small object code. We can do things like this. The example I have here, integer square root, was requested by somebody in the Japanese embedded systems industry. They wanted an integer square root, and so I did one, and I used it as an example for constant evaluation. So basically there, constant expression S1 is the square root, integer square root of 9. Even I could do that in the head. It's 3. But 1, 2, 3, 4, what would I do? I would calculate it in a calculator or on a doodle pad or something, and then I would type the result in. The problem with the doodle pad or calculator on the side is, one, there's a human involved, so there's a larger chance of error. Furthermore, once you have taken the constant and moved it into the code, only the constant is there. If something changes in for what you calculate, something you are dependent on, like the size of a word or something like that, now your program is broken when it gets recompiled with the changed assumptions. You have a magic constant. So I like to calculate it like that. And The low thing down here with weekdays is an example that shows we can abstract from the simple things like integers and actually use fairly powerful C++ abstraction mechanisms at zero cost. So I want to know the weekday of October 19, 2007, prints it out, fine. The interesting thing here is I can do a static assert. Let the compiler check that the weekday of October 19, 2017 is a Thursday. It'll do that at compile time, and if I guessed wrong about the day, the program will not compile. This is a non-trivial library. This, by the way, is going to be the 2000 C++ 20 date library that takes care of dates and time zones and other good things. And it's blindingly fast, by the way, as you can guess by the fact that we could actually do simple things. If we're only dealing with constants, we can do it at compile time. If we're using variables about days and such, and then it has to be done at runtime. But this is fast and simple enough to use for this kind of stuff. So we don't have to just deal with ints. We can do more complicated things. The other thing we do at compile time a lot is we select names, like I'm choosing a library there so I can switch from one library to another. I'm providing simplified names. There the storage is a vector of t. That's the storage I use for t's. And down here we are composing things, a policy is an executor, an allocator, so that I can say I want the policy that's sequential, and using the default allocator, imagine you're doing a multi-threaded system. That would be something like that. So a lot of this stuff is done in the type system at compile time to make sure we have a simple notation and a without extra overhead, extra calls. I mean, just because you have something that's user-defined doesn't mean you have to pay for it. The compiler can absorb a lot of that stuff. Here's an example, a traditional example. Here, I want a handle, and if I can put the things it's a handle to on the stack, if it's small enough, I use the on-stack way of allocating it. Otherwise, I use on-heap. I can compute that. Small objects goes on the stack, big objects goes on the heap. That in some cases is a very useful technique. The thing below there is using something called enable if in C++ in 11 and beyond. It says if t is printable, give it an operator, give the collection the operator output. So you can conditionally add functions to a class, which can be quite useful to get absolute minimal footprint of your code. That is about the ugliest syntax I ever saw. No, it's very ugly. I've seen much worse. But it does little thing that is useful of giving properties to types if and only if they can actually implement them. I'm not going to explain the details of this. You can look it up. There's quite a few books that'll do it. There are courses at this conference that'll explain to you how to read that one, so I'm not going to go there. What I'm going to do is I'm going to talk a little bit about how to write a driver. The traditional way of writing a driver in C++ is you have an interface with some virtual functions. So you interact through the driver to get the right operation. And so you can have driver 1, driver 2, and the user can use the appropriate driver without knowing what it is. Basically, you get a double indirection. You go through the driver. Driver goes to the virtual function table of the driver object, which gets you to the right operation there. So if you have, say, 15 or 50 electromotors in some gadget, maybe one of the flying ones, and they use different concrete drivers, but you can write your code that says just manipulate the electromotor through the proper interface. Things like that. That's usually good enough. But what if it's not good enough? What if this double indirection is killing your response time? Or what if the allocations that you go with this object-oriented style is painful in your system? What can you do instead? So let's just look. Oops. Let's see. I'll write a driver, and I'll write another driver. And then I'll say that for character devices, I will use driver 1. And by the way, those drivers take the device register as a template parameter. And the block device, where I'm using packets, I use the packet, and I'm using a different device register for that. So I'm really building in exactly what I'm doing. There's no polymorphism here, no indirections. I'm simply saying characters I write out using driver 1 on with the device register hexadecimal 80. Fine. So let's have a look. I'm now going to do something. I am using a data structure, a span, which is basically a pointer and a range, which is a really good way of passing things around, and it's also really good for simplifying code. It's really good for range checking if that's what you're doing. But basically, you can pass data as a pointer and a size. So I'm having a span of packets, sort of n packets for some n, and a span of characters. M characters, and I write the one out with the block device and the one out with a character device. Now the problem is that, yes, this is simple, but I have to know which kind of device I'm using all the time. Why can't it just pick the right one, which is what the polymorphism is for, what the standard interfaces is for, what we use virtual functions for. But you know, if I really know what I want at compile time, I don't need those indirections. So what I can do here is say I'm writing a writer which takes a span of t's, whatever t is, and if t happens to be a character, if constant expression is same character, and so that is the notation for saying at compile time check whether it's a character, that t is a character, then use the character device driver. And with the block device we use the other one. And you can see the code down there is exactly the same as the code as if I'd handwritten the calls to the specific driver. So there you have polymorphism without indirections, and it's basically optimal. And if you don't like the function calls to the two drivers, you can inline them. Sometimes that makes sense. If it's a simple driver, it makes sense. If it's a big, complicated driver, it's a dumb idea. But you can know that, you can look at it. It's really straightforward in terms of you're writing something and the assembler, the machine code, looks just right. So basically, if you want to program that way, you have to know what you're doing, but you end up using classes, templates, some aliasing. Quite often atomics and lambdas is common in this kind of code. Arrays and spans are common. They are array is a container that doesn't use any indirections. A span is a way of referring to a set of elements without any allocation, without any overhead. And be careful. I worry about indirections a lot. That has to do with the fact that a lot of what I'm doing has serious cache effects involved. Indirect function calls in particular are dangerous. That was why I eliminated them here. That, by the way, was a real example from a real gadgets that's deployed in the field, not from a big computer. And class hierarchies and virtual functions, be sure you need them before you use them, because there is a cost involved in them, and they bias you towards writing in a certain style of code, which usually involves more indirections and more allocations. And free store allocation and deallocation, usually I don't want to do that. Go to pools or stack allocators or something like that. That's much more predictable. Okay, so let's look at some more ordinary code. That is, assume you can use the whole language. Assume you're not really squeezed for time and memory. That you can be happy being twice or 50 times faster than the competition, but you're not actually worried about the last nanosecond. So let's do that. That's another embedded gadget from my definition of a gadget. It runs, I think, about 25 Unix systems, but if it gets it wrong, things go boom in very interesting ways, because what it does is to drill into rocks and then stick in explosives. Reliability is a very important thing. Basically, yes, I have said that. So basically, I would like to have type-rich code. I find that when there's more and more code, you need abstractions. You can deal with integers and pointers and such at a low level, but you can't read it. When you get much more code, when it gets into the 10,000, 100,000 lines of code, you need better abstractions. It just handles complexity better. And this shows a difference between two kinds of programmers, which I have labeled C and C++. And I've noticed that people with sort of the C attitude says, okay, let this thing compile, and now we can start the real work, which is debugging. I hate debugging. It's what burns my nuts, and that's not good. The C++ way is basically the compiler is your best friend. Express your ideas in such a way that the compiler can tell you when you screw up, because you do. We do. Okay, so different attitudes. So we want to structure the code in such a way that it's more comprehensible, more easy to check by the compiler, and that handles complexity scale better. Maybe the old way will work when there's 1,000 lines of code. It does not work with 100,000 lines of code. More opportunities for portability, better optimization. You can do compile time code as I showed you. And one of the main things here we do is resource management. A resource is anything that you have to acquire and then give back. And as we all know, giving back is harder to get right than to take. So we would like that to be implicit. In particular, in large code, I assume that if you have to give something back, you're going to forget it some of the times. At least I do. So that's fine. And so a resource should have an owner, usually a handler. So the general model is, here's something to represent ownership, and that's the owned thing over there. And we should make the acquisition explicit and the release implicit. That's the name of the game. Here's the classical example. Give me a file handle, use it, use it. It's very simple, and that's a well-known source of bugs. The problem being that you have to remember to close, and if you have a return statement or a long jump in C or an exception in C++ and that use F, you never get to the F close, and you have a bug. We need to do better. The problem is that just manipulates pointers, and you don't know what the point, well, if you're the author, you may know what those pointers mean. You may know that something comes out of F open must go back into F close. The documentation says so, but you didn't read it. Neither did the compiler, so it can't help you. And so we do something like this. We create a handle, explicitly the type handle, and it says you open the file. If you can't open it, it throws an exception. You can have several ways of opening a file, and the important thing is the destructor there. It closes the file, so we can now write the code simpler. Just give me a handle to the file called S, with read permissions. And however you get out of that block, you get the file closed, and that's simple and safe, and it's pervasive in the C++ standard library, has been for 20 years and so. And there are still people who don't want to use it because they say usually that exceptions are evil or something like that. I don't think they're evil. We need error codes and exceptions. If a failure to do something is normal and expected, okay, let me check it. Get an error code. And if the immediate caller can be expected to handle the problem, that's fine. That's what error codes are for. But we have a lot of cases where errors are really rare and therefore likely to be forgotten. So for those of you who use printf, when did you last check the return value of printf? Because sometimes it fails. In particular, if your system is running and with a network file system or something like that, or you're writing through a socket, the write can fail. And if your fprint wasn't checked, you have a bug, latent bug in your code. So I really dislike having to remember to check error codes because I forget. And the more unlikely the error is, the more likely I am to forget, and the harder it is to find the bug because I didn't think about it. Error propagates up to an ultimate caller. Quite often in a system there is a place where errors are handled. Quite often it's quite near the top of the system. If anything goes wrong, get me up here. Clean up any messes if I can, otherwise write out some log information and then you can either bomb out and try and reboot, something like that. That's quite common. But if you have to percolate your error through 15 function calls, then you have 50 cases where you get an error indicator plus a value. You have to check the error indicator and then use the value. You do this 50 times. The answer is no, you don't do it 50 times. You forget, so you do it 48 times. And now the propagation is broken. So I worry about that. No suitable return path. I mean, if I do A plus B, where's the return path for the error handler? There are many things. So basically, I think we have to choose in big systems. We have the nuisance of having to decide whether an error is an error or some exceptional condition. And how do we do that? There's some guidelines for that, but here is my thing. It has to do with overhead and be able to remember and forget things. There's an implementation overhead for exceptions with a normal implementation if and only if the exception actually happens. That is, if most of the times there's no exception, nothing happens. It's fast. If an exception never happens, which should for most programs be for most exceptions, you actually don't have any cost. If you have virtual memory, the whole mechanism can be sitting out in the virtual memory. This makes it very costly to do your first exception. It has to then go and grab all the mechanism that you hadn't been using before, so don't use this for hard real time. But look, if you can afford a millisecond, you can probably afford even the most expensive exception, and most of the time they don't happen, and after you've done the initial initialization, it actually will happen. So there's a simple experiment that I've done repeatedly and other people have done. Go n levels deep in a call sequence and then report an error. And you can do that with exceptions, you can do that with error codes, and so which is the more expensive? It's really, if you do that experiment a couple of times, you will find that sometimes error handling is with error codes is really much faster and simpler. I mean, it's only level is 1. Error codes tend to win big factors, not little percents. If you go down 1,000 calls and the error handling happens The error happens infrequently, like 1 in 100. Exceptions win hands down for performance. And it's a naive thing, so how rare must an error be to be considered exceptional? That's actually a question I tend to ask myself a lot, and it depends on a lot of things. C++ exceptions were designed assuming an answer to that exercise with about 1 in 100. That is, if an error happens more than 1 in 100 times you call down there, it's not exceptional. You better deal with it specifically. This is not where you just say, oh, something happened. Whoops, somebody deals with it, which is what the exception thing does. And it works rather nicely, and it takes care of the cases where you go on network and things like that. Okay, so when you use exceptions, try not to have try-catch in your code. That belongs in implementations and just at the top level. If every level tests with try-catch for whether there was an exception in the function you called, you should have used error codes. If you really want explicit checks all over the place, error codes is just the same as try-catch. Try-catch, you can use that as a very slow, ugly way of writing if then else. Don't. It just drives you nuts. This is not Java. You do not have to have a try on everything where an exception can propagate. And so just show an example. Here is a mutex. As a matter of fact, there are 2 mutexes that are standard, and there's one I designed myself. And I can do access like that, scope, log, access data, implicit call. That doesn't have any exceptions in it, but it's still RAll. It is a general idea that you initialize something and it's implicitly released. So you can't say that you don't use RAll because you are not using exceptions. You can use the general style of initializing an owner, use the stuff and implicitly release even if you don't use exceptions. That's scoped lock, that's a C++ 17 feature, and that is the way you acquire 3 mutexes without danger of deadlock, because you will not proceed beyond that point unless you have all 3. So it's obviously implemented, try the one, try the other. If you couldn't get the third, back off again. And that kind of technique. Very neat kind of stuff. If you really can't use exceptions, my main example is flight controls, because you can never afford the unpredictable exceptions. If we had tools that could measure the maximum propagation time, we could use it, but I haven't been in that situation. So you can introduce a notion of a valid object, and so where you would have thrown an exception before, you don't set the valid bit, and so you can write for all of your code, open the file handle, check it was valid. Now, it's not as pretty as throwing an exception, and you still have the problem, what on earth do you do if the file handle wasn't valid? You can do something for a file handle, but if you have to do it with all of your resources for whenever you acquire some memory, say, it becomes a real pain to have all of those error handle code there, but you sometimes have to do it. So basically, for ordinary code, you can use most C++ features. The STL containers come in really handy. I always start with a vector and don't use anything else unless I have a good reason to. The good reason may be that I'm doing lookups, so I need a hash table. That's called an unordered map. But basically start with those containers unless they are, unless they don't work. Unless there's a problem with it, you don't need to go any further. It's a good start. And then you can optimize. Exceptions are fine. Chrono for time, and if you need time zones, use date. It has just been voted into the standard. You can download it from the GitHub for it. The name is Howard Hinnant. who's a really good guy, and if you can remember that name, you can look it up on GitHub and find what is going to be put into the standard. Actually, it was voted in. So it'll come in 20. Exceptions are fine. Lambdas, I haven't gone into lambdas today. They're really useful for things you do, code you execute only once. You only call once. And for parameterizing things to make your applications more flexible. Auto to stop repeating. The range for is really useful for writing simple loops, and most loops are simple. For all x in v, do something to x. That's simplification. It actually matters. When you're looking at the code, it's easier to read. You don't have to worry somebody's messing with a loop variable or something like that. It's slightly less error prone. And if you have to do anything that's really critical, you have to look at the things that are not predictable in the sense that you can guarantee they run in a fixed constant time, usually short fixed constant time. New or malloc, throw, runtime type identification. STL containers use new when you grow them. So either you have to be careful to set them up before you start the engine. You can't have new and delete in a program that's supposedly last forever, because you can get fragmentation. So you need something like pools. Avoid std function. It may contain a malloc. So basically the first rule of thumb is, for really critical code, don't do anything that does a malloc. If you have a malloc, you need a delete, a free. If you need a free, you're going to get it wrong with a high probability. Furthermore, it costs something, and if you get fragmentation, you may not last forever. Okay, keep simple things simple. For my opinion, simple means simple in quality code. It does not mean the lowest level facilities. It's fairly easy to tell people to use a macro and a void star and an int. The problem is that it's also very easy to make bugs at that level that cannot be caught by any analyzer or compiler. So you want to get up with that. And so simple does not mean low level. I mean simple in real use. And you can do anything with low level features, and that's exactly the problem. I mean, why don't we use goto? The answer is it can do anything. We want something that's better behaved, like a for loop or an if statement or something like that, or an algorithm at the next level. So that's it. And build on a sound foundation. That is, work a lot to make sure that the foundation is solid, that your abstractions are solid, that the libraries you use are appropriate for your task. Don't spend all your time on the statues and fancy cannons up on the high decks, because you may get into trouble. I am actually using this picture to scare the standards committee from putting too many fancy features on instead of working on the foundations. But that's a good story, that one. I am about to run out of time. I'm good. Okay, so then I'm going to tell you a little bit about what we're trying to address here. The standard tells you what you can do and what it means. Like, this is undefined behavior. The standard will tell you all of that. It doesn't tell you what is good code. And the language is big and complicated, and you need guidance. I need guidance. And so we are trying to attack the problem of, in the terms of, what would you like your code to look like in 5 years? Like, just like today is not a good answer. It's not good enough. We can do much better than what we are doing today. We're very proud of our code today, often, but we know we can do better in 5 years. We know if we could use all the facilities of the language, if we use them better, what would we like to do? And we are tackling the problem in terms of a cocktail of problems: language design, coding rules that says what is good, libraries for easier writing code, and static analysis for enforcement. So the basic idea is that the way the doctors kill illnesses, sometimes one medicine isn't sufficient, but a cocktail of them will kill whatever it was that ailed you. And so we're trying to do that combination there. The targets are type safety and resource safety problems. We want to eliminate those. We want to go after known complicated techniques. You look to the web and there are no shortage of people showing how clever they are. And that leads to complicated code and complicated techniques. We would like to point out when this has gone overboard. I mean, the way I optimize code these days is first I throw away all the clever stuff. That's usually the complicated stuff. It's the one with all these fancy pointers going left, right, and center, and clever uses of multi-core, things like that. Get rid of all of that and see if it's good enough now. If not, we start building the clever stuff back again, but in a reasonably good way. So we go after overcomplicated techniques, known bug sources. Bugs hide in complicated code. Bugs correlate with certain uses of code, so we try for that, and known inefficiencies. And so this is the core guidelines. It's a joint project between quite a few people. It's open source. The main players is Morgan Stanley, Microsoft, Red Hat, Facebook, and there's a lot of people adding in. This is a very interesting group. I mean, Red Hat and Microsoft in the same meeting, a joint project. This is good. There's progress. And what we're after is what I showed on the previous slide, but in particular, I want to get type and resource safe C++. Absolutely no violations of the type system, no leaks of it. No leaks, no memory corruption, no garbage collector. If you don't generate any garbage, you don't need a garbage collector. No limits on what you can say. I want it to be C++ and very expressive. No performance degradation, and I want it in C++ because, well, I don't want to write another language. It takes too much work. And we want it tool enforced, and we can't quite do that. The latest I've heard is that the Microsoft Static Analyzer, which is part of Visual Studio and should be separated out as a program you can run by yourself, but they haven't done it yet, can catch essentially all dangling pointers. So anything you ever saw with a pointer pointing to something that wasn't there should go away at compile time. Actually, static analysis time, you run the static analyzer whenever you feel like it. So this is being tested on million-line programs. And so you can find it there on the GitHub. It's called C++ Core Guidelines. And there's a tiny support library like the span I showed you earlier. That's actually, we're trying to get that into the standard because we think it's our business to put the GSL out of business by making what is useful part of the standard and what turned out to be not useful, which I hope is nothing, to go away. So that's basically it. I'm not too happy about the support for embedded systems programming. Like I've never written a real program in this field that didn't need a pool. So I write my own pool every time, or rather I fish out my old pool and modify it. I don't want to do that. I shouldn't have to do that. There should be better library supports like pools and stack allocators should be standard. Some flat data structures should be in there instead of the chained one. Why don't we have a flat map? And the answer is that the standard library was designed by people who thought free store allocation was cheap and that linked structures were good. Well, with caches and with constraints on memory and allocation, that's not good enough. Also, the guidelines are quite weak on embedded systems programming. We are trying to deal with that. There is a group in the standards committee led by Mike Wong from CodePlay. He used to be at IBM. It's called the Study Group 14, Games and Low Latency. If you're interested in this kind of stuff, think about enjoying this one. And it seems less embedded than formerly. A lot of the financial types have joined for the low latency, so we actually need more embedded systems programmers to build this. And the purpose of that group is to come up with a list of things that will be useful to standardize, mostly library things, and then guide the committee in that area. And so that's something that's coming up. I had hoped to be more specific about this, but I ran out of time, as could be expected. So basically, that's what I wanted to say, and I hope we have time for some Q&A. Thank you. 5 minutes. Any questions? Ow. Yes.
Some point of the talk, you have said that in safety critical applications you shouldn't use malloc or memory in the free store, but you can do that before, for example, in an airplane before the.
Oh yeah. Yes. Yes. You can use free. Yeah. Repeat the question. I said that you shouldn't use malloc and free in critical systems. That's right. Especially free. Because if you use both malloc and free, you can get fragmentation. But as you correctly pointed out, the rules very often is during startup you can allocate memory, provided you can prove that you didn't run over, and a runtime check will do that. And so it's quite common that during startup you can do new or malloc, but never delete, because fragmentation is not predictable.
Is there any way to enforce that the programmer is not violating that condition, that once you enter the main loop, is any way to enforce that you are not using?
Is there any way of enforcing the rule against new and delete? And the answer is, in the language, no. But there are static analyzers for sale and for free that can do that.
You can just hash define new and delete to something that will stop the compiler, and then just if-def the main.
No, he says just if-def it away. No, that will not work because you need it during startup. Furthermore, new and deletes can be hidden very cleverly in other code. The place I mentioned earlier that bit a lot of people was that inside std function, which is the abstraction that can hold anything executable, there lurks a malloc. And so if you just, instead of using pointers to function, use std function, which is much more elegant and safer, etc., you get hit by mallocs. And it's not that easy. But there are static analyzers that are pretty good at it. Well,
all right. Thank you very much.
Thank you.